Thanks for tuning in to this presentation about the tracking of Antarctic calving fronts. First, a little bit about our project. This research is part of the Helmholtz AI for Cold Regions project, or AI Core for short, a collaboration between the German Aerospace Center, Alfred Wegener Institute, and TU Dresden. The project encompasses 4 geoscientific use cases that all use remote sensing data to gain insights in polar regions. Today, we will be talking about how we can use deep learning to track Antarctic calving fronts. Let's look at the task at hand. Our goal is to monitor the Antarctic coastline using remote sensing data. This analysis should take place with high spatial resolution as well as a high temporal frequency. We decide to use SAR data for this task because optical data has a number of drawbacks for this application. The challenge of clouds is especially rough in the Antarctic, where it can be hard to differentiate clouds from ice. The phenomenon of polar night obstructs optical vision for a large part of the year, which defies our goal of high temporal resolution. SAR data doesn't suffer from these limitations, so it was chosen as the primary data source for this project. Based on this premise, we conduct experiments to see how well this approach can work. We have collected a dataset of Antarctic coastline scenes from the Sentinel-1 mission at 40-meter resolution from June 2017 to December 2018. Our experts have manually delineated the glacier calving fronts, resulting in annotations for a water class and a land class. After splitting the data, the scenes have a combined area of around 500,000 kilometers squared for the training set and around 200,000 kilometers squared for validation purposes. To tackle this task, we start by training a baseline model on this dataset. We choose the widely used UNet architecture as a starting point. After our initial training runs with this model, we make some observations. First of all, this task requires a lot of spatial context information. In this example picture, there are 2 large icebergs floating in front of the coastline. They belong to the C class, even though they look very much like land ice. Now, these structures we're looking at are huge. Our baseline model simply cannot look at a large enough spatial context to come to the right conclusions. The model's classification for this specific pixel will only be based on input pixels within the green square. Visualized like this, it is understandable that the model cannot see the icebergs for what they really are. Fixing this isn't too hard. We go back to our model architecture and make a little room in the middle. Adding additional down and upsampling layers, like this, greatly increases the receptive field. After this simple modification, the context window increases that it almost covers the entire scene. With a bigger spatial context window, the model will have a much easier time to correctly detect the coastlines. The next observation we make is that the task isn't actually well defined. Up until now, we just assumed that we need to segment the scenes into water and land. But maybe that's not the right way to do it. Maybe we need to look at the edges instead. Taking a step back, it seems impossible to decide what is the right way of defining this task. So instead of deciding for one or another, we simply train the model to do both segmentation and edge detection at the same time. Model-wise, we just add a second output layer for the edge detection task. Finally, we notice that among the scenes in our dataset, most are very easy to classify correctly. However, there are the occasional outliers where coastline detection is really hard. We keep score of how well the model is doing for each training scene. Then, we selectively train it on the hard examples that it is struggling with the most. You can think of it like a flashcard system for training deep learning models. So now, let's look at some results. In the top row, you will see the results for edge detection, and below that the results for sea-land segmentation. Baseline denotes our initial UNet approach for segmentation and a state-of-the-art detection network, HED, for the edge detection task. We can see that the changes we conduct greatly reduce the blur present in the baseline segmentation. At the same time, the knowledge of the sea and land classes helps the model output better edge predictions. Therefore, we are confident that our model can help with the large-scale analysis of Antarctic coastlines. Thanks for watching.